Okay, thermochemistry. The word thermo meaning heat, and chemistry, of course, chemical reactions, is what we're going to be studying here. Alright, to start this off, we need to just talk about the energy basics. That is to say, what is energy, what is heat, how does it apply to a chemical reaction, and such. Alright, so first of all, energy. Defined as the capacity to do work or to heat something up. And so heat, often symbolized by Q, and work by W, are both related to energy. They're not energy themselves, although they have the same unit as energy. All right. Again, energy is the capacity to heat something up or to do work. All right. So energy is the thing, and heat and the work are the evidence of that thing. There are many different types of energy out there, such as kinetic energy, the energy to move something, or if something is in motion, it has kinetic energy, we'll say, and the faster it goes, the higher the kinetic energy. Potential energy, that's particularly interesting to chemists. Potential energy is stored energy. Now, potential energy could be a rock being held up high. Of course, that's in a gravitational field, and the higher you go, the more potential energy it has. And if you want to think about it, the more energy it took to get it up there, right? Or you could have other types of potential energy, such as chemical potential. That's where you've got a chemical molecule, atoms, who are at a higher state of energy. They are storing that energy, just like the rock being held up high is storing that energy, and it could be released. Now, in that sense, it's being released in a chemical reaction, such as gasoline. You combust the gasoline, you release a lot of energy. That energy can be converted then into the motion of the car. It also comes off as heat. The engine gets pretty hot. Alright, electrical potential energy, there's that. Nuclear potential, a lot of different types. But again, we're going to concentrate on the ones that apply to chemistry here. In the figure here, we've got potential energy of this water that's storing up high, just like the rock. And as it's allowed to drain down here to this lower level, it is able to release that energy and, in this case, convert it to electricity. Right. Thermal energy is the one that's directly related to heat. Right. Thermal energy, for a chemist, we need to understand where is it, what is its source, what does it actually look like, if you will. That thermal energy is the kinetic energy. But it's the kinetic energy not of the bulk, but of the actual individual atoms and molecules that make up that substance. Of course, they are rotating, they're vibrating, they're tumbling, they're translating from one side to the other. All of those types of molecular motions are what we're talking about. The faster they go, the higher the kinetic energy they have, and we would say that that substance has more thermal energy. Alright, so high thermal energy would be a hot substance, or low amounts of thermal energy would be a cold substance. To measure that thermal energy, we need to talk about temperature. This was actually introduced way back in chapter 1, but temperature will measure that thermal energy, that is to say the kinetic energy of the molecular motions. We can have different scales that temperature is measured at. Fahrenheit, the old one, we're not going to use much. 32 is where water freezes, 212 is where it boils. It actually was defined as something slightly scientific, I suppose. The coldest he could achieve in his lab at that time, that's what he called 0. Of course, we can get even colder than that, we recognize now. And water froze at 32 on that particular scale. Celsius and Kelvin are the two that we're going to be using the most often. Celsius, convenient because on that scale water freezes at 0 and water boils at 100. So that makes a lot of sense. It's nice. It's 100 degrees between the freezing and the boiling of water, water being very plentiful. And so there you go, 100 degrees on that scale, where over here on the Fahrenheit that was 180. See, so the size of a Celsius unit is actually larger than the size of a Fahrenheit unit, which is smaller. Okay, on the Celsius scale, we can get down colder than 0, yes, and so we can go down to negative numbers on that as well. Kelvin is the actual SI unit of temperature. Kelvin takes the same size unit as Celsius, so if I have a change of 5 degrees, that's going to be the same size as 5 degrees on the Kelvin. Celsius and Kelvin being the same, that is. However, we slide the scale. We keep the size, but we slide it down so that 0 Kelvin is actually the coldest that you can possibly get. It's called absolute 0. How can we have something that goes to absolute 0 and not get colder? That may not be obvious at first, but if you think back again, we're talking about the motion of these molecules, the kinetic energy of molecular motions. And so the slower they're vibrating, the slower they're tumbling, the colder it gets. Well, what if we get it all the way down to where they stop moving? So they're not vibrating, there's no motion. Well, you can't get any colder than that, and so we call that 0 on the Kelvin scale. Absolute 0, can't get any colder. So both Celsius and Kelvin are going to be useful. We're going to use those kind of interchangeably, not so much on Fahrenheit. Over here and in the book we do give ways to convert from one to the other. So if you have Fahrenheit and you want Celsius, we first subtract 32 off. That brings the zeros back in line, if you will, and then we multiply by the conversion difference for the size of a Fahrenheit and a Celsius. So subtract 32 and then multiply by 5/9. That'll give you Celsius. You could turn that around and solve it for F. If you want to go from Celsius to Fahrenheit, you're going to multiply by 9/5 and then add 32. All right, but we're not going to use that a whole lot. However, these two right here, very, very useful. Yes, we are going to use those an awful lot. And so from Kelvin to Celsius right there. If you have Celsius and you want Kelvin, just add 273.15. Or if you have Kelvin and want Celsius, subtract 273.15. See, we don't need any multiplying because the size of the unit is the same. All we have to do is slide the scale up or down essentially. And so we'll be using those quite a bit. Alright, now we can get to the definition of heat. Remember, heat itself, while it has the same units as energy, it actually isn't energy. Heat is the flow of energy from one thing to another. And it always flows from the hot body to the cold body. So if I have an ice cube and I drop it in boiling water, the heat is the flow of that thermal energy from the hot water to the ice cube. And of course we're going to cause that ice cube to melt when that happens. So it always has a flow, it's not energy itself. So they have to be in contact too, those two bodies. So in this example, or this figure, I'm sorry, from your textbook, we've got a hot and a cold substance, H and L, high and low I suppose for the temperatures. If you bring them in contact to each other, now we can exchange that thermal energy, and the thermal energy is flowing from the hot to the cold, as the arrow implies, and it'll continue to flow and continue to flow until they have the same amount of thermal energy. Right? So we have heat here because it is flowing. At this point we no longer have heat because they're not flowing. You see, something will feel hot to you because that thermal energy is flowing into your hand. Or if something feels cold to you, it's because the thermal energy is flowing out of your hand into the substance. Right? You have to have that flow. Once you reach the same temperature, well, it's not going to feel hot or cold to you because there's no more heat because you're at the same thermal energy. Okay. Exothermic, a couple definitions for you, and endothermic. If you have a process like a chemical reaction that releases heat, that is to say it's hot, and so if you touch it, boom, it's going to flow from that beaker into your hand, for example. Right? So it's going to feel hot. That's what we call an exothermic process. An endothermic process, on the other hand, it absorbs heat. So that's like a cold pack. You know, when you break it open, you want to put it on your injury, break it, and it gets cold. That's an endothermic reaction. That reaction's happening inside that pouch is actually absorbing energy, and as it does, well, it's got to come from somewhere. And if your skin is touching that pack, well, it's going to flow out of your skin into the pack, and it's going to feel cold to you then. We sense that as hot flowing in, or heat energy flowing out, we sense that as being cold. So hot and cold is just the direction that that heat is flowing. All right, units. Important to be able to measure these things and you have the right size units. Again, any energy at all, whether it's potential or kinetic or chemical potential or whatever, has the same units. It's energy, therefore. It's just different types of energy. Heat and work as the flow of that energy also has the same units. One of the oldest units that we'll actually use is the calorie. CAL for the abbreviation, and that was defined back with water again. It said, hey, if I have exactly 1 gram of water and I want to raise it 1 degree Celsius, how much energy would that take? That amount, or that chunk of energy, is what we call 1 calorie. Alright, so a calorie is defined as, again, the amount of heat required to raise 1 gram of water by 1 degree Celsius. Good definition, we use it all the time. It's based scientifically. You'll also see a food or a nutritional calorie. Technically, that's really nothing new. A food calorie is just 1,000 of these normal calories. Or you could rewrite that as a kilocalorie. A food calorie is just a kilocalorie. Now we abbreviate a food calorie with a capital C. So if you have a packet of cookies or whatever and it says, hey, there's 400 calories in this, that's a food calorie, capital C. It's actually 1,000 calories, the normal base unit. So it's not, it's not 400, it's 400,000 calories. That sounds pretty scary, and so they go kilocalorie instead, but then they just use a capital C instead and call it a food calorie. We won't use that a whole lot. A joule. Now, a joule is the actual SI unit of energy, named after the scientist, Joule. It is defined as a compound unit on other simpler SI units. Technically, it's a Newton times a meter. A Newton is a force, and so a force applied over a distance, yeah, that's actually one way to define work, and that is the unit of energy. So a Newton meter, and of course a Newton is a kilogram meter squared per meter per second squared. I'm saying that wrong. So when you multiply that by a meter, you get the SI base units of a joule, a kilogram meter squared per second squared. It's a little foreign perhaps, but it does work and it's consistent. What we need to know for sure is how do you interconvert. I already talked about calorie to food calorie. That's just 1,000. From a joule to a normal calorie, 4.184. 4.184 joules is the same thing as 1 calorie. Okay. Now, different substances do have the ability or different abilities to hold heat, to hold energy, if you will. And that's because their different atoms and molecules have different connectivities, different crystals, different ways that they connect to each other, intermolecular forces, and so they have a different ability to vibrate or to rotate. And again, that's thermal energy, that's what we're talking about here. We can measure this in lab by using heat capacity. Heat capacity will be defined then essentially as, well, how much energy can these things hold? Right? A heat capacity, capital C, C for capacity, capacity is defined as the amount of heat per change in temperature. Usually in SI units that would be joules per degree Celsius, or again, because the size of a Celsius unit is the same as a Kelvin, you could say joules per Kelvin. Right? That would be heat capacity. So how many joules does it take to raise that substance by a degree of Celsius or Kelvin? Very similar to what we kind of talked about back here with a calorie. We took a gram of water. We said, hey, how much energy does it take to raise it 1 degree Celsius? We call that a calorie. So it's similar to that, right? The heat capacity. Now, a large hunk of metal would take a lot more energy to raise it 1 degree Celsius than a small hunk of metal. And so to even that out, to say, well, what is a constant value for that metal? We could do it 2 different ways. We could divide it also by, well, the size of that metal given in grams or any other unit of mass. So in particular, joules per gram degree Celsius. We've taken the normal heat capacity and just divided it by the size of the sample. That's called what we call specific heat capacity. In the equation form, little c here for specific heat capacity is Q divided by m delta T, mass and the change of temperature. All right. Recall, and I have this up here in the notes, recall that when we say delta T, that means the change of temperature. So the final temperature minus the initial temperature. Remember, anytime we have a change, it's always final minus initial. And so, change in temperature. Molar heat capacity, that's another way to even this out a little bit. Instead of dividing by the grams or the mass of the substance, here we divide by how many moles of substance do we have. That's a perfectly good way. Many textbooks will put a little bar over the variable, so bar C or C bar here would mean the molar heat capacity, and that's Q over N, N meaning the number of moles, N times delta T. Okay, I think for most chemical problems you'll see the specific heat capacity is the one that's usually used. All right. Here's a table from your textbook showing the different heat capacities, or specific heat capacities, which means it's per gram, of different substances at 25 degrees Celsius, which is room temperature, and 1 bar, a bar meaning pressure. So that's essentially 1 atmosphere, normal atmospheric pressure, in other words, 1 bar. Bar, by the way, is the same thing as like barometric or barometric pressure and such, so a bar. Alright, different substances you can see have different heat capacities. Water is pretty high, not quite as high as helium, but water 4.184, going all the way down here, and there's some very small ones like down here, lead and gold, not very much. So those guys, they're more locked into their crystal structure. They don't really absorb, or they can't hold as much heat. Which means if you give them the same amount of energy, their temperature is going to go up a whole lot more than, say, if you give water that same amount of energy. Water, having a higher heat capacity, has the greater ability to absorb and hold that heat, that energy, where something like lead and gold, not so much. Which is why water is great as a coolant, say in the radiators or in the coolant system of your car. It can really absorb a lot of energy without itself getting crazy hot. Other substances wouldn't work as well. Alright, so again, these are specific heat capacities, and you'll be needing these type of numbers when you do the various problems. 5.1 asks, a flask containing 8.0 times 10 squared, in other words 800. 800 grams of water is heated, and the temperature of the water increases from 21 up to 85 degrees Celsius. How much heat did it actually absorb? Okay, well, 800 grams of water heated from a temperature initial to a temperature final here. We can use the equation for heat capacity. Remember, the specific heat capacity, let me just write this over here. The specific heat capacity, C, was defined as Q over mass change in temperature. I can turn this around and solve it for Q, actually. It would be C times M delta T, which is what I've got right here. C times M delta T. Get rid of that now. And plug in the numbers for mass. Well, it was 800 grams. C, the heat capacity, the specific heat capacity, we get that from the table up here for water. It looks like 4.184. So I plug that in, and the units, joules per gram degree Celsius, and that is given in the head of the table, joules per gram degree Celsius. Always watch your units, of course. And then delta T, so temperature final minus temperature initial. And a good idea is to always check, make sure your units are going to cancel. I've got a delta C on the bottom and a delta C here from the change in temperature, or degree C, excuse me, not delta. I've got a gram on the bottom, a gram on the top here. Those will cancel. The only thing that doesn't cancel is joules, J. And so my answer will be in joules. Multiply that on your calculator, 210,000 joules, or 210 kilojoules.